Welcome to the Virtual Reality Reconstructionist, the show where we explore the fascinating intersection of technology and safety and how your work is helping to save lives and prevent crashes. I'm your host, Roger Ryan Ryder. I'm excited to be here with you today. Now, on with the show. Most of today's information is covered in the NIJ document, Best Practices for 3D Scanning and Virtual Reality Documentation of Crash Scenes. This NIJ document came out in 2023 and covers numerous areas of best practices, such as terms and definition, which we covered in episode 1, technology overview, which was covered briefly in episode 1 as well. Today we're going to discuss the remaining sections of the article, which does a great job on best practices. The sections consist of equipment calibration, equipment validation, personnel capabilities, training, experience, and qualification, TLS data capture, data processing, data management, and disclosure of data. So let's start with the reminder that the Virtual Reality Reconstructionist is focused on public safety, crime, and crash scenes where terrestrial LiDAR scanner devices, also known as terrestrial laser scanning devices, TLS, acquire complex geometric data that capture a three-dimensional representation of a scene. This technology is used in criminal justice applications such as documenting such scenes. Although the use of this technology is increasing in criminal justice application, no standardized vendor-neutral guidelines for use are currently available for end users until now. The NIJ has partnered with the Forensic Technology Center of Excellence in a terrestrial LiDAR scanning working group to create consensus-based best practices to standardize and improve the use of application of the TLS in scene documentation and reconstruction. This guiding document intends to establish a minimum standard for capturing, processing, analyzing, visualizing, presenting, and storing TLS data in a forensic context. This resource, the paper we're discussing, was built to promote uniform implementation and use of TLS technology in practice. This will ultimately improve the practitioner's ability to attain scientifically supportable conclusions from TLS data, ensure effective quality management procedures, and improve presentation of the information to stakeholders, including law enforcement, investigators, and the courts. Again, we covered Section 1 and 2 in Episode 1, so we'll start this episode with Section 3, which is equipment calibration. We're talking about defining calibration. It's a set of operations that establishes the relationship between values of a measuring instrument or measuring system under specified conditions, or values represented by a material measure or a preference material, and the corresponding values realized by standards. When it comes to calibration, public safety has not planned for future equipment needs on TLS systems. Sometimes it's an oversight, other times the system is purchased with a grant and the calibration charge in the future is overlooked. Instrument calibration will necessitate ongoing cost and downtime for the agency and owners. The cost for the certified calibration will be significant and should be budgeted in advance. TLS devices are complex measurement devices that are susceptible to degradations in their precision and accuracy over time. The rate of measurement degradation depends on several factors, including quality of the instrument construction design, the components, frequency of use, care and handling and storage, and exposure to harsh elements. Over time, this will affect the instrument's ability to produce measurements within the vendor's specifications. Most importantly, the TLS operator and 3D analyst must know the measurement of certainty associated with the data they capture and exploit. This is critical to the ultimate admissibility of 3D evidence produced by the TLS. So next, let's talk about calibration frequencies. Vendors have specified an interval between the instrument's calibration. It's usually a period of 1 to 2 years based on the instrument's design and expected deployment environments. Most TLS device users operate in the architectural, engineering, and construction or land surveying industries, and calibration recommendations are set for these specialties. As a result, TLS manufacturers' recommendations for calibration may not be suitable for forensic applications. Let's talk a little bit about self-calibration. TLS devices with internal collimation checks have recently been developed and made available for purchase. These devices purportedly do not need calibration and are described as self-calibrating. More research and validation are required to substantiate these claims. Manufacturers' white papers are available on this topic and represent a good starting point for further research. As of this publication, the calibration is only recognized as described in this section, and TLS performance should always be compared against an external reference. Equipment validation. This section of the document provides an overview of TLS equipment validation considerations. Performance of a forensic TLS device should include an instrument validation at periodic intervals for monitoring and traceability purposes. The instrument is tested to verify or validate the performance specifications published by the manufacturer of the instrument. Instrument validations can be performed in between calibrations to ensure the instrument is ready to perform with the existing tolerances. Two of the most burdensome and overlooked challenges on the ongoing success of a TLS program are the recurring costs of the instrument downtime associated with adhering to some manufacturers' prescribed period of calibrations and maintenance. Implementing a method that can be used to demonstrate that the instruments used to collect data were functioning with instruments' published tolerances even in the absence of a manufacturer's calibration certificate could help reduce instrument downtime and maintenance costs associated with a recurring calibration. This in-house validation method, sometimes referred to as the periodic calibration verification. This verification, according to the International Organization of Standards, ISO, is as follows. Field procedures for determining and evaluating the precision of terrestrial laser scanners and their ancillary equipment when used in building, civil engineering, and surveying measurements. Primarily, these tests are intended to be field verifications of the suitability of a particular instrument for the immediate task at hand, and to satisfy the requirements of the standard. They are not proposed to test for acceptance or performance evaluations that are more comprehensive in nature. For limitations of ISO 17123-9 reduce its applicability to this task, notably the layout of the test field described in the standard is based on the maximum manufacturer recommended distance for the capturing targets. For an instrument with 75-meter targets capture distance, the target used to create the vertical triangle on the test field would be placed at 37.5 meters above the height of other targets. This requirement limits the location of which the test field can be placed. Additional reference values for target distances are not captured as part of the test. Therefore, skill errors in the instrument being tested cannot be evaluated. So, manufacturer's procedures. Manufacturers may include tools and procedures to facilitate periodic user verification that measurements taken by a TLS meet specifications. Users should verify with the manufacturer of their specific TLS that use of such tools and procedures are suitable for extending recommended service intervals for devices that are functioning properly. So now let's get into personnel, capabilities, training, experience, and qualifications. This section describes the different functional practice levels of personnel when capturing and using TLS data, provides the suggested and recommended minimum educational and training requirements for each level of functional practice, and recommends training content and proficiency testing levels. So functional levels of practice and TLS data. Operators operate the instrument to capture TLS data that are acceptable for a particular analysis. Personnel that appropriate instrument settings. These personnel operators select the appropriate instrument settings to capture the required details and placement of the instrument to cover the scene with minimal occlusions and with minimal number of scans required. They also qualified to testify about instrument operation and how it was used to capture TLS. Maintains the instrument, which includes moving the instrument, calibrating at appropriate intervals. Moving on to a technologist, they have the qualifications of an operator and those listed in this section as well. Processes the TLS data using the native or non-native software, has the ability to integrate TLS data with data from other devices or sources to produce demonstrative exhibits, including measurements. And they're qualified to testify about how the applicable software was employed to process the data into a demonstrable product and can provide measurements for that data as needed. And next is the analyst. Has the qualifications of a technologist and those listed in this section as well. Uses TLS data for other applicable sources of data to complete specific forensic analysis and renders expert opinions or forensic reconstructions. Qualified to explain their reconstruction methodology and render expert opinions or conclusions about the reconstruction and the respective discipline. Minimal training requirements for these positions. So operator has received a manufactured prescribed course of training in the operation of the specified TLS instrument and has demonstrated a level of competency in the proper operation of that instrument to collect TLS data that also meets standards established by the organization. It should also be proficiency tested in instrument operations as a part of an ongoing quality assurance program. Technologists have received a manufacturer's prescribed course of training in the operation of the TLS instrument and has demonstrated a level of competency in the proper operation that the instrument has collected TLS data that also meets standards established by the organization. May have received an additional manufacturer prescribed course of training in the operation of the non-TLS devices or instruments whose data may be used in conjunction with the TLS data and has demonstrated competency in the proper integration of non-TLS data sources. They've also received a manufacturer prescribed course of training in the use of native and non-native software and have demonstrated competency in the use of their available software to produce demonstrable renderings of the scene using single or multi-source instrument data. And they should be proficient testing in both instrument operation and software use as a part of an ongoing quality assurance program. Then we get into analysts, which should have the same qualifications as an operator and technologist, and they should be proficiently tested in both instrument operation, software use, and construction methodology as a part of the ongoing quality assurance program, and have received requisite training in a particular area of forensic analysis in which conclusions and or opinions are being drawn from that data. Examples of that would be trajectory, blood spatter, crash momentum, crash analysis. So proficiency testing, operators, technologists, and analysts should be proficiently tested in their level of competency every year as part of an ongoing agency or employer quality assurance program. Proficiency testing should be tests that a representative of the casework where the result is known or casework that is directly observed and monitored by personnel qualified at the same or higher level. Results of proficiency tests should be maintained by the agency in accordance with agency procedures and guidelines. So now into TLS data capture. This section provides an overview of TLS applications and considerations for scanning scenes in a field setting. Applications for 3D data. TLS is used to capture a scene by documenting evidence and its location with respect to other items in a scene. The location of evidence in relationship to other objects is often important, such as in shooting scenes or in bloodstained patterns are considered. Items of interest may include bloodstained patterns, bullet impacts, environmental topography and surrounding environment, footwear impressions, location and position of decedents, tire marks, vehicle or property damage, wounds, weapons, and witness viewpoints. More specifically, TLS can provide measurements for 3 types of applications. Critical measurements, which require a high level of accuracy and are used to inform the expert opinion in areas such as bloodstain pattern analysis, crush analysis, and trajectory analysis. General analysis are used to take overall measurements where a rigorous level of accuracy is not required, such as skid marks and sightline distance. Demonstrative use is when measurements are not the primary consideration and the data is simply being displayed to show the overall lay of the land. So now we're going to get into considerations for preparing for a TLS scan. Before using your TLS instrument in a scene, operators should note the following considerations for preparing for a TLS scan. Establish the security of the scene itself. The scanning records the scene elements as closely as possible to how they appeared at the time of the incident, and, when possible, the scene should be secured before it is scanned. One technique to secure a scene is considering 2 perimeters, an outer perimeter for staging equipment and personnel, and an inner perimeter surrounded the area to be documented. To the best of the operator's ability, the inner perimeter should be kept free of people until the scanning is complete to ensure evidence and the surrounding environment is not disturbed or obscured. Understanding the scanning order of operations. Laser scanning is one step in the overall process of scene documentation. Because laser scanning has a low impact on the scene, it is recommended that laser scanning occur earlier in the documentation process. Once experts have photographed and marked the scene and evidence, it should be scanned before anything is moved. All known evidence must be marked before scanning. The environment may play a significant role in how the scene is captured. Factors such as poor lighting, tight spaces, rain, fog, or other weather conditions will dictate the scanning settings, and the capture method should be adjusted accordingly. High and low temperatures can affect the instrument's measurement accuracy or ability to capture data at all. Operators must ensure their instrument is functioning as designed in the current conditions to take proactive steps to mitigate these impacts. Rain, depending on the instrument's IP rating and rainfall rate, can damage the instrument and/or add extraneous noise to capture data. Rapid changes in barometric pressure can also produce errors in some instruments' elevation calculations. In cases where weather and other factors such as rapidly deteriorating evidence are a factor, the capture setting may need to be adjusted to record as much of the evidence as possible while it is safe to do so. When scanning on a steep slope, operator safety and instrument stability will also need to be considered. Preparing for reflective objects. Reflective objects or surfaces can introduce artifacts due to reflection and/or refraction when scanned by a TLS. Therefore, there are multiple ways to prepare a reflective surface to ensure they can be measured. A large mirror can be covered with a sheet or of paper if there is no evidence in the mirror. Sterilized surgical drapes may also be used in place of paper as a contamination minimization measure at scenes. Other reflective surfaces can be sprayed with a substance that will leave a residue. Dry shampoo, fingerprint powder, and aerosol deodorant that contain baking powder are 3 examples of easily available products that will leave a residue to assist the scanner with collecting the data. If the surface is going to be prepared this way, ensure any forensic evidence is collected and photographs have been taken before preparing the surface. Understanding the intended use of laser scan data. In many cases, underlying the end use of the captured laser scan data is important because it will dictate the necessary instrument settings and area to be scanned. For example, if scenes require precise measurement analysis such as bullet trajectories or bloodstain patterns, require scanning with high-resolution instrument settings, whereas cases required only general measurements or planned drawing, color data or high-resolution scan settings may not be required. In addition to the desired end visualization should be considered because camera fly-throughs, animations, and virtual tools or models are better served with higher resolution color scans. So mounting your scanner appropriately. TLS can be mounted in several different ways to ensure proper coverage of a scene. The incidence angle, which is the laser beam makes with the surface, affects the instrument's ability to correctly sample the surface. The measurement precision error increases as the angle between the laser beam and the surface decreases. There is less measurement error if the laser beam is more perpendicular to the surface being measured. Next up is the set of appropriate point density for data needs. For data used to obtain critical measurements, the point spacing should generally range from 1 to 3 millimeters. 1 millimeter is about 1/8 of an inch at the location of the measurements. For general outdoor scenes, the point spacing should be no more than 15 centimeters, which is about 6 inches, at the point of reference. Because each scanner has different settings and different scan modes, the operator should ensure the point spacing meets or exceeds the manufacturer's guidelines when performing the scans. The operator should thoroughly know how their instrument functions and its capabilities at the range in question. The Reference Measuring Protocol, RMP, is an on-site validation that should be performed every time the TLS device is deployed during a forensic investigation. There are several acceptable methods for performing the RMP. The RMP process compares the TLS measurement to the same measurement taken with a separate instrument. Often this comparison is done using a known length artifact that is introduced into the scene, such as a set of targets or prism pole, or an easily characterized distance in the environment. A corner-to-corner room measurement that is measured by both the TLS and a handheld laser electronic discharge machine device would be an example of an acceptable RMP. A NIST traceable length artifact measured by TLS and compared against the certified length of that artifact is another acceptable RMP that has the added assurance of using an object calibrated through an accepted third party. These reference measurements should be accomplished using a NIST traceable standard object. There are multiple ways to accomplish this measurement. A NIST certified tape measure can be used to measure between two easily identifiable points in the scene, which can be compared with a measurement in the scanned data. An object that has been measured NIST certified tape measure or a manufacturer-specific NIST certified measurement device can be placed in the scene, and its known measurement can be compared to the measurement in the scanned data. TLS manufacturers may market these devices specifically to scanning. Objects placed in the scene should be placed in the first and last scans in areas that are out of the areas of evidentiary value. They should be placed in such a way that the measurements test the accuracy in all three measurement planes, X, Y, and Z. Operating your TLS instrument at the scene. Best practice is to understand the capabilities of TLS or line-of-sight instruments. Objects closer to the scanner may hide objects behind it. The operator must ensure that the scanners are placed to minimize hiding areas of interest. The operator should understand that the scanner will see and use the scanner's perspective to ensure the scene is properly documented. In some circumstances, scan locations do not need to be far away from each other to achieve full documentation of the scene. In other circumstances, the scanner location may only require a change in elevation to ensure this is accomplished. Scan overlap. When the data are to be registered using cloud-to-cloud registration, there should be sufficient overlap between scans. Certain scanning environments will require the use of artificial common reference objects, more commonly referred to as targets. Scanning environments that are devoid of rectangular architecture or planar flattened objects will need the addition of targets to register individual scans together. If the data are going to be registered using targets, they should be a minimum of 3 targets in common between each scan as recommended by the manufacturer. Avoiding places targets collinearly or coplanarly, meaning the heights and surfaces upon which targets are placed or the heights of the tripods supporting the spherical target should vary. Multiple types of targets can be used for registration. Scanning with color and using external lighting. When using external lighting to capture color, avoid shining lights directly into the laser scanner, which can cause the color to wash out. Ideally, exterior lighting is placed under the scanner or in a manner that does not cause the color to be overexposed. Field notes are recommended. Scanning operators should document their actions in field notes. These notes should record any information that is important to the scene, including such information as the date, time, on scene, case number, your name as an operator, weather conditions, scanner make and model, as well as the serial number, date of last calibration, scanner settings, types of targets used, reference measurements used, scene diagram with photos showing scanner positions or targets, location of known critical measurements, anything that might have an impact on the collection of data, references of scan positions, scan plan, reference sketch, and position or location of reference ties for repeatability. Data processing. Best practice of data collecting with TLS must be processed for use by analysts. The degree to which the data is processed will depend on its intended use, but common steps must be taken to obtain repeatable outputs accurately reflect the scanned subjects. Data import. For most TLS data from a scanned project must be imported into a proprietary software for processing. During import, filter options may be available. The user must understand the effects of these settings on the quality of data and select the appropriate level of filtering for the intended use of the data. Now let's go into registration. Registration is defined as the process of determining and applying to two or more data sets the transformations that locate each data set in a common coordinate system so that the data sets are aligned relative to each other. Registration combines the point clouds captured at multiple scan locations at a site into a single common point cloud representing the entire site that was scanned. Registration may be automated or any required manual alignment of scan positions data or manual matching of points that are common in the different scan positions. The registration software may provide feedback on the quality of the registration, but the user must visually verify the quality of the registration accuracy by examining the alignment of common surfaces or the correspondence of common points. Regardless of the density of the data collected, errors in registration may significantly reduce the accuracy of distances measured between points scanned from different positions. Outlier removal. Because a TLS will collect data from an object within its range, including people and vehicles moving around in the scan scene, it may be necessary to remove points from the transient objects to improve visibility of evidence in environments. Care must be taken to remove data of evidentiary value from the point cloud. The point cloud includes all reliable data points to present the most accurate depiction of the scene. Important clarifying language for the data reporting or presentation should include caveats such as extraneous and unreliable data recorded during the scanning process, such as artifacts caused by reflection, edge artifacts, people, and objects moving within the scene during the scanning process have been removed for clarity. Data that have been removed are available for examination upon request. Revision history. While processing, registering, and removing outlying points, each major step of the process should be documented. A brief description of the actions taken prior to saving point should be recorded and later reviewed for repeatability. The raw data should always be saved prior to any processing, and each processing step should be documented externally on the software or within the registration software itself. Ideally, the manufacturer software would automatically record users' input and processing of the data sets. However, at the time of publication, this feature is not available at any manufacturer known to the authors. Last known section we're going to cover is the trial preparation. Trial preparation for involved parties is important. Litigators should understand the necessary questions to be asked to lay the foundation of the technology. In this documentation that we're going to give you a link to, there is some suggested questions in the appendix if you want to review that. The scanner operator who is called to testify as a fact witness needs to have a component working knowledge of the technology, including how the TLS works and the underlying principles of the data collection, processing, and registration. When a courtroom demonstration is conducted, all TLS equipment, computers and software should be charged and up to date prior to the trial date. Any demonstration should be rehearsed in advance with an attorney present, the TLS data for admission. That's all for today's episode of the Virtual Reality Reconstructionist. If you enjoyed the show, please be sure to subscribe and leave us a review on your favorite podcast platform. And if you have any feedback, suggestions, or questions for us, you can reach out to me personally at ryan.ryder@rrinvestigations.com. Please note that the view and opinions expressed in this podcast are solely those of the host and guest, and do not necessarily reflect the views or the opinions of the Virtual Reality Reconstructionist, its affiliates, or its sponsors. Thanks for tuning in. Stay safe and stay curious.